Thank you. I'm a minute early, but that's good because my PDF takes about a minute to load. So, and we're not going to count that as part of my designated 45 minutes that Eamon is very desperate for me to keep to. And if it doesn't load in a minute, we'll go to the copy one, which doesn't have the JavaScript running in it, which opens immediately. So what am I going to talk about today? So when I was invited to speak here, I was like, well, not really sure why I've been invited to talk. And then I was a bit worried, which for some of you won't be a surprise. And then I was like, well, okay, I guess I have used a computer at various points and not just to send emails. And then I sort of got thinking a bit more, and I sent Culver an email and said what I thought I would talk about, and she said that sounded like a good idea. And then I wrote my abstract, and then Eamon came into my office and sort of berated my abstract for a while. So then I rethought it. No, I didn't really, Eamon. I did exactly what I thought I was going to do. And then I decided I should do it with slides because of what I wanted to talk about, and then forgot how long it takes to write slides. And so I finished at about midnight yesterday, and then I checked them this morning. But I mean, a large part of it took this little number here. So this is going to count up to 45, which is my time limit from when I opened my PDF. And if it works correctly, which I haven't tested because I haven't had it open for 45 minutes, it won't crash my computer, and that's not for sure. And secondly, it should change color as I get to a certain percentage through my time. So I should point out I didn't actually make that. There is a LaTeX package called TD Clock, which claims to do that for you. And if it doesn't, those are the people I'll be blaming. OK, so an outline. Yeah, so I want to tell a story. Because it's Wednesday morning, and so people don't want to hear too much maths. They'd rather hear a story. So it's not a sort of traditional story. It's a story of the subgroup structure of exceptional algebraic groups. And I've spoken about that always, sort of every talk I give almost. But today I want to concentrate on something different. So usually when I'm talking, I would explain lots of things. And then at the end, the sort of parts of the proof, I would just brush under the carpet and say, oh, yeah, I do this, this, and this. And I might mention the fact that I used a computer, or I might forget about it. But today I'm going to concentrate on these computational interludes. And roughly speaking, this is what we'll cover. But that's not really so important. So yes, so the hero of our story are going to be these computational interludes. And so I sort of want to say thank you to everyone that's ever done anything to do with groups of Lie type, Lie algebras, representation theory, machinery. Because certainly to do my work, I've needed it. And so Derek mentioned in his talk at the introductory workshop that he was always striving for a push-button algorithm. And I never heard it called that, but I was really glad that he does look for such things. Because then in Richard Parker's talk yesterday, I thought, oh my God, there is no way on earth I'm ever going to be able to use the metax based on what he was talking about. I mean, yeah, it's just not for me. And then fortunately I realized, oh, but I do use the metax all the time. It just happens to be embedded in Magma, and I don't have to worry about whether my matrices are defined over some field and then worrying about what the compiler is telling it to do and other things. So in fact, I wanted to make a little plea. Could you make the button a bit bigger, a bit brighter, and with instructions? So something like this. And then I decided, well, if I'm pushing the button, maybe it should look something like this. OK, so let's actually start. So once upon a time, there was an exceptional algebraic group, just like all good fairy tales. And of course, it's defined over an algebraically closed field. I don't want to worry about finite fields. And my characteristic is going to be P. So if you're not too familiar with these exceptional algebraic groups, there's 5 of them. So there's G2, F4, E6, E7, and E8. And today, it's not going to be so important if you don't know what these are. At times when I'm talking, you can just think of GLV. And although it won't be true, what I'm saying, it certainly has the right sort of feel about what we're doing. So subgroup structure. So the exceptional algebraic groups were sad. No one had fully understood their subgroup structure. And so for today, our question is to ask, what are the reductive connected subgroups of G? Don't worry, the story metaphors soon die out. I got bored of doing them. And I mean, I should emphasize the word fully. So by the time I started considering this, and I can pinpoint the date, it was the 4th of October 2010. and it was when I first went to Martin's office for my first supervision meeting, and he wrote down the question I was going to study for maybe just the start of my PhD. I think I answered it about 8 years later. So, but it starts, as always, we're standing on the shoulders of giants. So Dinkin answered this question in characteristic 0 in the 50s, and then work of Seitz, Testament, and Liebeck Seitz completed it. So this theorem looks really, I couldn't find a better way of saying it succinctly without having to write more words. So apologies for that, Martin. But essentially, we do know all of the connected maximal subgroups. We know more than that, but for today's talk, that's what we're interested in. So as an example, if we take E7, so I think Martin even briefly went through this algorithm at the introductory workshop, but don't worry if you weren't there. So I draw my Dinkin diagram of E7, and then I draw the extended one, and then I just start putting my hand over parts of the diagram. And so I put my hand over this one, and I see a root system which looks like A1D6, which is that one there. And then I put my hand over this one, and I get an A7, and I put my hand over this one, and I get an A2, A5. If I wanted the 7 parabolics, then I don't do that, and I put my hand over one node at a time through the diagram. Okay. But then there are more, and those ones are slightly more difficult to define. Those ones are quite natural. And so, yeah, we do understand plenty about the subgroup structure of exceptional algebraic groups. And today, because I want to focus on sort of techniques in the proof, I'm not going to give much background as to why we care. Usually, if I was talking, I'd say we sort of use them to understand the subgroup structure of finite groups of Lie type, or give a theorem of Richardson, which talks about affine varieties. But I'm going to suggest that people probably care enough about the subgroup structure here not to worry about affine varieties. Okay, so again, I'm sort of contractually obliged when I give a talk to talk about Serre's notion of complete reducibility. And it's a really beautiful, simple idea. So I have some subgroup X of GLV, so a faithful representation. So I can talk about just maybe my subgroup X being irreducible, if V restricted to X is irreducible, or indecomposable, or completely reducible. And the idea is I just want to take GLV and replace it by G. So some other reductive algebraic group. And then the question is, what should we change our definition of irreducible and completely reducible to? And so it turns out that without too much thought, you can change from worrying about the V we had in GLV to just considering parabolic subgroups. Parabolic subgroups in GLV are stabilizers of flags of subspaces. And again, in a usual talk, I'd spend a few minutes going through the equivalence of the definitions. But for today, it's not so important. So a subgroup is G completely reducible, GCR, if whenever I find my subgroup X of G inside a parabolic subgroup P, then it's actually contained in a Levy subgroup of P. And if you plug in G as GLV, you get the same definition as before. And similarly, a subgroup is said to be G irreducible. It's sort of the easiest way of being G completely reducible. You just never live in any proper parabolic subgroup. Okay. So I did look up what a good story has, and apparently plot development is one of the points. So this is plot development. So we want to find all the reductive connected subgroups of G. And we can split this now into two problems. So I discussed, so the GCR subgroups, they're the ones that when they're in a parabolic, they sit there nicely. They live inside a Levy subgroup. So we can classify the GCR connected reductive subgroups, and we can classify the non-GCR connected reductive subgroups. So I guess in Richard Parker's point of view, we've split it into two subproblems, although we haven't really split the work up at all. I've just given a name to one half of the problem and another name to the other half. But we can remove the word reductive in GCR. It turns out that in characteristic 0, GCR and being reductive are the same thing. They're not in characteristic P, but GCR subgroups are certainly reductive. And can actually replace 1 by saying, if I'm nicely in a parabolic, i.e. I'm in a levy, then I can push my subgroup all the way down until it can't be pushed any further, which means it's irreducible in some levy. So to classify the GCR ones, we need to classify the L-irreducible connected subgroups, so the ones that don't live in any parabolics of L, for each conjugacy class of levy subgroups. And the levy subgroups are reasonably easy to understand. At least we can look at our diagram and just cross out more nodes as we go. So part 1, GCR subgroups. So again, I don't really want to concentrate too much on what the theorems say. I actually want to look at how we do them. So I should apologize to Alastair, because this is even worse than the statement of the theorem of Martin's. So part 1 is done when L is a proper levy. And this is not in chronological order either. So we did this after this work, even though it has a question mark. That's just because the memoirs of the AMS have a nice backlog. So I think I actually finished it in about 2016. And so what this says is, so the first theorem says I have all of my GCR subgroups when they're actually reducible, when they live inside a parabolic. And the second one says I understand the ones for an exceptional algebraic group. G is always an exceptional algebraic group in this talk. I understand the irreducible ones, so the ones that don't live in a parabolic. And the answer for the second theorem is about 50 pages of tables. They're tables not made by a computer. I should emphasize that part, because many times when I speak about the length, someone says, oh, that's nice. You just got Magma to print out 50 pages of tables. Sadly for my life, no, I could not. And they're painstakingly made by hand. And they could be shorter, but they're written in such a way to hopefully be useful. And we'll see what I mean by that when I talk about how we're going to find the answer. And so the question is, how do we do this? How do we find all of the G irreducible subgroups? But I thought I'd check what Richard called it, and it's how do you do something? That was his statement. So here's the strategy, which is relatively simple. It's just the steps in it don't turn out to be all that simple. So we're looking for all of the subgroups, all the G irreducible subgroups that don't live in a parabolic. And we have this list of maximal connected subgroups. And I can look at my list, and I can throw away the parabolics, because they live in a parabolic. And that's what this reductive maximal connected means. I had many conversations with Martin about the order of these adjectives and whether that meant something different. So to be clear, there should be a hyphen. These are maximal connected subgroups which happen to be reductive. They're not maximal amongst reductive subgroups. They're not connected subgroups that are they are maximal connected subgroups which happen to be reductive. So you take the list that I showed you before, and you just throw away the parabolics. And then for each maximal subgroup you get, you do the same thing. Now, my maximal subgroup, so this line hides, well, about 2 years of understanding in my PhD for how to actually do this. So the maximal subgroup you get, when we were looking at E7, there was an F4 and a G2 which cropped up, but most of the others were of classical type. And so to understand their maximal subgroups, there's another theorem of Liebeck-Seitz, which gives an Ashbacher-style classification of the maximal subgroups. But you have to, the nice thing about the exceptional ones is there's only 5 of them. So usually when people do something, they write them all down for you. And there's unfortunately infinitely many classical groups, so people don't tend to write down everything. Mainly because we don't understand the representation theory to be able to do that in generality. So you do have to input some things, and you have to understand how to use Frank's lovely tables that tell you what dimension certain representations are in low characteristics, and understand the geometry of the classical groups. But let's just say for today that if I take one of my maximal subgroups of my exceptional algebraic group, I can understand how to, again, find its reductive maximal connected subgroups. And then again, and again, and again, and again. So you just keep doing this, going down. So you take your first maximal subgroup, you find its reductive maximal connected subgroups, and then for each one of those, you do the same thing, and again, and again, and again. And then I end up with a list of candidates, curly C. So M1 will be my first candidate subgroup X1. then I find all of its reductive connected maximal subgroups, their subgroups, blah, 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 and then I get to M2. And I do the same thing again. But that list is ludicrously large and just not correct. So we have to cut it down. We want it to contain only one copy of each G-irreducible conjugacy class. So there's two things we need to do. First, when is something in that list G-reducible? So I kept going down and finding maximal subgroups that didn't live in parabolics each time, but that doesn't mean they didn't live in parabolic back in my big group G, or even my group M. And when are two things in the list G conjugate? And I want to talk about how I used or abused the computer to do both of these problems. So let's start with B, to be traditional. So when are two subgroups in my candidate list conjugate in G? Well, we need some group theory. Okay, I'm sort of trying to concentrate on the computation. But a moral of the story, it's easier to prove things when they're correct. So I'd like the computer to sort of give me a good idea as to whether I can expect two things to be conjugate. So how am I going to do that? So here's where the computer first enters the story. Well, if x and y are conjugate, I don't think I'll be telling anyone anything new, to tell them they act the same way on all of my G modules. So if I can find the composition factors of the action of x on the Lie algebra and or the minimal module, and in fact I'd like those anyway, as part of the information I'd like to give about these irreducible subgroups. If I find x and y in my list two different ways, but I see they have the same composition factors, then I think, okay, I have to do a bit more work, and probably they end up being conjugate. In fact, a theorem first due to Liebeck and Seitz in slightly large characteristic, like bigger than 7, and then extended by myself to these irreducible subgroups, tells you eventually, after all of this work, that if you find two subgroups in the list once you've removed anything that's not irreducible. So if I have my list of irreducibles and I look at all their composition factors, if I find two coincidences, it means the subgroups were conjugate, apart from one example in E8 with some A2s that I'm not going to go into. Okay, so yes, here we can use Magma to help us do that. I'm not going to, much to Eamon's delight, I'm not going to start getting Magma up and typing things in. He was worried that I'd be a two-finger typer and be very slow. He didn't give me much credit. I mean, I would have had it typed out already in a notepad file. So here's a way I can find two. This is sort of the first silly example. So my maximal subgroup A2, A5, which we saw before in E7. So we can just think of that as an SL3, SL6. But SL6 contains SP6. So I can take A2C3 as a maximal subgroup of A2, A5. And then SO3 is a maximal subgroup of SL3, as long as P is not 2. So I get down to this X, A1C3. But then a really silly way of being able to do that another way, but in my list and in my algorithm, I also take the maximal subgroup A1, A5, because I first took an A1 maximal subgroup of A2, and then I take the C3 inside A5. And here it's pretty obvious that X and Y are the same subgroup. And I don't want to be worrying about that. So I claim it's not difficult to remove these duplicates. Again, maybe was difficult in my PhD for a while, but now we can pretend we just understand G conjugacy in each maximal subgroup M. And I need G conjugacy, not just M conjugacy. I might have some triality that's conjugating my B3s together in a D4, but the triality only lives in F4 rather than B4, for example. So here's a slightly more non-trivial example. So I take my same subgroup X, this A1C3 and A2A5, and now I've found an A1C3, or I've found lots of them, inside an A1C3 inside A1D6. So this A1C3 acts as a tensor on the D6. Again, it's not too important, the details. But this one's slightly more difficult, because they live in two different maximal subgroups of E7. But we can still walk through the quick proof. There's an involution on top of the A2A5. This A1C3 is the centralizer of the correct involution. And then you calculate that the centralizer of that involution in G is A1D6. I would actually probably do part of that on the computer. You don't have to. But then which subgroup of A1D6 is it? I mean, which subgroup of A1, A1C3 it is not immediately clear. And in fact, there are two classes of A1, A1C3 and A1D6. because there's no graph automorphism on top of the D6 and E7. So here's where we need some representation theory again. We need to be able to understand the composition factors of one or the other of them. So we want to understand the composition factors of X acting on the minimal module V56, and then if we understand the composition factors of all the subgroups of A1, A1, C3, then we can find which one is correct. And so, okay, we start from this decomposition, which is given in the memoir of Liebeck and Seitz when they classified the maximal subgroups. They also gave you lots more information. And so without a computer, I can understand how to decompose. This is just the natural module for A2, and it's dual. So when I put SO3 inside SL3, I just get a high weight 2. Again, P is not 2. But then when I want to restrict A5 to C3, when I actually wanted to write this up yesterday, the easiest way I knew of working out what the module structure of the wedge cube of the natural for C3 was to ask Magma, for P being at least 7. And then I went to Frank's tables and checked that I needed this P not equal to 3, because otherwise a 0 slips out of this factor, and I end up having to add that on. And there are other examples which are even more complicated where I at least needed the computer. Okay, so what about part A? So when is X a reducible subgroup? So I've got my candidate list, and if I was clever, I threw away things that were conjugate to each other before I started worrying about whether they were reducible or not, to save myself some work. But at the end of the day, I really need to throw away the ones which aren't irreducible. The whole point was to get a list of the irreducible subgroups. So sometimes this is straightforward. So let's take F4. Again, I don't want the characteristic to be 2. That's not true in the paper. The hardest ones are the small ones, but we don't want to be doing messy things on the slides. So I can take a B3 inside D4 inside B4. Or, if you like, a sort of easy way of thinking of that is to take an SO7 in an SO8 in an SO9. Then the centralizer in B4, or the connected component of the centralizer in B4 of B3, is a one-dimensional torus when P is not equal to 2. And again, it's quite easy to see that if you think of it as the SO7 in SO8 and SO9, I get an SO2 as my centralizer, which is a one-dimensional torus. And why does that tell me I'm reducible? Well, if I have to be G reducible, then I should have no connected centralizer. And this is the one proof of the talk. So suppose I have a torus inside my centralizer. Well, then X lives inside the centralizer of that torus, which is a levy. So it lives inside a parabolic. So we don't want that. So our centralizer must be unipotent, but then X lives in the normalizer of that unipotent group. And that's contained in a parabolic by the Borel-Titz theorem. And I didn't attribute that, but the first place I saw it written down was in a paper of Liebeck and Tessler. Okay, so the take-home is that if I can already see something like a obvious torus, once I've started going down my steps, I've sort of gone too far, then I want to throw it away. So in particular, I can assume I've thrown out all M reducible subgroups. So I started with my M1, I took the maximal subgroups, I took its maximal subgroups and its maximal subgroups. It's not surprising that if you keep doing that, eventually you're not going to be irreducible in M. You're going to live in a parabolic of M. And of course, once we see one of those, we stop, because you can't escape the fact that your overgroup lives in a parabolic, then you live in a parabolic. So problematic cases. So what's our predicament? Well, let's say the composition factors, which we now know we can calculate, suggest X should be banished from our list. But its connected centralizer is 1, or unipotent, and I can't see an obvious group that it normalizes or centralizes. Well, we want to find this unipotent subgroup it maybe normalizes, because then the normalizer of unipotent subgroup is in a parabolic. So here's an example which took me a long time to work out. So I have this G2F4, a maximal subgroup of B8, okay? And then when P is 7, I get a maximal G2 inside F4, sort of slip down from E6. And then I can take a diagonal one. And I want the one with no field twists or anything like that. And you stare at it for a while and you think, well, okay, it actually looks like it should be in a D7 parabolic. So I can find a G2 inside my D7 levy, calculate its composition factors, and see that they match. So if it does live in a D7 parabolic, then it should normalize a 14-dimensional unipotent subgroup. But I don't know how to go to Magma and just say, I've got this subgroup, which I can just about build as a finite subgroup. Can you find me all the 14-dimensional unipotent subgroups that it normalizes? I mean, maybe you can do that, but my guess is you can't. So instead, we look in the Lie algebra. So we build a finite version, S, say G2 of 7, of X, which lives inside E8 of 7. Then we prove it stabilizes the same spaces as X on Lie of E8. So how do you do that? Well, sort of been many iterations of a similar statement. Essentially, you want 3 conditions to hold for this. So the composition factors of your module, in this case Lie of E8, the composition factors for X, when you restrict to your finite subgroup, they shouldn't break up. There shouldn't be any coincidences that you didn't have for X for S. And the X groups between them should be nice. So if I had, so they should be injective from when I think of them as groups for X to when I think of them as groups for S. But essentially, you can just think of, this is some technical condition that if the composition factors are right for X on Lie of E8 and S, so I might needed to have taken 49 here rather than 7 to get them to hold, but luckily I didn't. Okay. Then, well, now I have S in the computer, and I have the Lie algebra of E8, well, E8 of 7, but that's okay, it's essentially the same thing. And then, apparently, it can do linear algebra, which is great. So I can check that S fixes an abelian ad-nilpotent, turns out exponent 3, subalgebra of Lie of E8. And I care that it's of exponent 3 because then I know I can exponentiate this subalgebra and find something unipotent, which has, well, I didn't mention it, but it's 14-dimensional. That was kind of an important part. And then I know that actually X fixed this abelian ad-nilpotent subalgebra. So when I exponentiate it, X normalizes my 14-dimensional unipotent subgroup that I wanted. Yeah. So I didn't say anything else apparently on this slide. So that's it. So we kind of we were able to use Magma because of the fact that we had a nice module where the finite group and the algebraic group fix the same subspaces, and also because we can do linear algebra a lot easier than we can do computations in 248 by 248 matrices. Okay, so that was a way of, I had a subgroup that was in my candidate list, and I stared at it for long enough, and I decided, no, it really shouldn't be in there. What if I, and I managed to put it in a parabolic? Well, if I can't do that, then sort of if the subgroup will not come to the parabolic, then the parabolic must go to the subgroup. So instead, for the last part of the talk, I want to say how we go to sort of the other part, these non-GCR subgroups, and we sort of dig around in our parabolic and we find a reductive connected subgroup that we think looks like the one which came from maximal subgroup M3, and then we sort of understand all of the subgroups in the parabolic and hope we have some nice way of deciding that it actually ends up being conjugate to the one in M3. Which, when you say it out loud, sounds a bit silly. Like, why on earth could you not just take the one in M3 and show that it lives in a parabolic? Well, I just couldn't. And maybe you can, but there were a lot of long conversations with Martin in his office about this case, and this was eventually how, between us, we came up with a way of doing it. So indeed, we have a candidate X in M and G, a strong suspicion that X is contained in a parabolic. So we're going to go to the parabolic P, understand its subgroups, and try to force one of them to be contained in N. That last step is non-trivial, but we'll skip it for today's story. But it was used to deal specifically, for example, with a case of an A2 and A2A5 and E7 when P is 3. So we're going to go hunting for non-GCR subgroups. So to remind you, they're the subgroups that live in a parabolic, but they're a bit mysterious. They don't live in any conjugate of your Levy subgroup. So I have my Levy decomposition, P being QL. And let's just, for sake of ease, say that we're hunting simple algebraic groups in P. Well, we can always project such a subgroup to the Levy. And what this allows us to do is say that we're going to take all L-irreducible subgroups of L. We'll call them X bar. And we want to find all of the complements to X bar in QX bar. Now, complements is in inverted commas, is you have to be slightly careful at the algebraic group level what you mean by that. David Stewart has a whole paper, I think George McNinch does also, about worrying about the Lie algebras intersecting nicely so things work out scheme theoretically. But we're not going to worry about any of that for today. What we are going to have to worry about is cohomology. So I'm asking to find all the complements to x bar in qx bar. Well, that sounds like a cohomology question. And so we want to find this, well, usually I would call it a cohomology group. But Q is not normally abelian. So we only get a pointed set rather than a group, whatever that is. I mean, I do know what it is, but we're not going to care about what it is for today. Instead, we're going to try and break up Q into abelian pieces and then actually do some normal cohomology and then sort of wave our hands and pray that we can put it all back together again. So algebraic sites give us this nice central series of Q. So this thing Qi mod Qi plus 1 is central in Q mod Qi plus 1. And so we call this a level. I'm going to quickly skip that part about what it's made up of, but essentially it's combinatorial from the parabolic you chose. So if you put your hand over one of them, you end up knowing, well, you know pretty much everything about this series just from the root system. And what's even stronger is that L, my levy, acts on each of these levels. So now that's abelian, and it turns out it's actually a module for L, which is nice, because we're going to have a way of understanding the cohomology of L acting on one of its modules rather than just some non-abelian group. And the root system even tells you which modules you get. So my brilliant timer says that I have 15 minutes left, so I probably won't give too many examples. But here's another point where we use the computer. So if I take an A1 levy of E8, then it turns out that has 27 of these levels, and you'll find 100 and something, 122 dimensions worth of Q to put into all of these levels. Now, I personally don't want to do that by hand. I probably can't do that by hand without making too many mistakes. And so, fortunately, it's something to do with the root system. And Magma's really handy with root systems, and it understands all of them much better than I do. And so we have a small program that will just spit out all of these modules for you in each of the levels. And what next? So now we've got these levels. So they're modules for L, and they're sort of they break up Q into sort of pieces, and we want to understand each piece first and foremost. So let's say we know what module this level is restricted to L. Then I'm going to say that we know what the level is restricted to X. Well, it's not quite so straightforward, because X might be some interesting irreducible subgroup of L, and it's not clear that you can just go around restricting their modules. If so, then we'd sort of understand quite a lot of things which I don't think we understand in generality, but I might come back to that if I have time at the end. What we do need to calculate is we take each indecomposable summand of our level, let's call it M. Our level is a module now for X. We take each summand, and we want to work out this H1 cohomology group for, that should be an X bar. Now, if they're all 0, well then, happy days. You have absolutely no non-standard complements. Everything is conjugate in QX bar to X bar. And so if we were actually started out, we wanted a non-GCR subgroup to get it back into our M3. So we wouldn't be so happy in that situation. Unfortunately, that's not an if and only if. So I can have some non-zero groups coming up in these pieces, but then well, other things get in the way, and it turns out you still don't get any non-standard complements. So how do we calculate these H1X bar M's? Well, hopefully someone's done it for you. And we're dealing with small rank subgroups. I mean, I'm always inside a levy of E8, so I'm at most rank 7. And when M is irreducible, we're usually OK. But there are plenty of times where our M is not irreducible. And again, computation enters. So what we want to do is construct the same module M for a finite group of Lie type S of P to the A of X bar. So in the talks already, we've seen that essentially in defining characteristic, the representations of this finite group of Lie type are the same as my algebraic group, as long as I restrict the weights I'm interested in. And I pick A big enough so things don't obviously go wrong, whatever that means. And then I just ask Magma for the cohomology group. And if I've not done something silly, which is plausible, then it usually works it out for you. Or someone will say, Adam, yeah, that's not going to finish in the lifetime of the universe, let alone in the next coffee break. So you probably want to think again about doing that. OK, but on this occasion, we've worked something out for the finite group of Lie type. But it doesn't tell us necessarily anything about the algebraic group. But if we're in a really lucky situation, then there's a theorem of Klein, Partial, Scott, and van der Kallen, which tells you you're done. So actually, the cohomology is quite nice, and as long as there's certain conditions on the weights hold, you can say, OK, I've done a calculation for the finite group of Lie type, and it actually tells me it's the same for the algebraic group. Unfortunately, the times where we're struggling to calculate these tend to be exactly the time where this theorem, unfortunately, tells you nothing. And otherwise, you start using long exact sequences and hope you find the right tricks so you don't have to go to the dark side. So one is a friend, not you. And the dark side are things like spectral sequences and other things. And then they maybe become a former friend. I don't know, David, are we still friends? OK, so here's an example. So for E8, when P is 2, I can look inside a D7 parabolic, OK, and I can take a G2, which acts this way on the natural module. That's what VD7 lambda 1 is. So T of 1 naught is a trivial over a 6-dimensional module over a trivial in an indecomposable, and then I can Frobenius twist it. If that's not something you're happy with, don't worry. This will be over soon enough. So if R is non-zero, then I get something irreducible, which was my condition. I wanted to be hunting these things in such a way that x bar was irreducible. Okay. Now my D7 parabolic has 2 of these levels, and I want to understand the action, the cohomology of the module for G2 on both of them. One of them happens to just be this, and I understand that. There is no cohomology. The other one is one of the half-spin modules. And it turns out, because I live in a B3, B3, I know I act like this. So I have the tilting module tensor, the twist of the tilting module. And Alastair and I stared at this for a while and really weren't sure what the answer should be. So again, you just ask Magma for some small values of R. And then when it tells you the answer is 0, you have a bit more confidence that you should be proving it's 0 rather than proving it's 1-dimensional or 2-dimensional. And yes, it did take a while to prove this. We didn't have to go to the dark side of spectral sequences, so that was nice. But knowing it was true for the finite group was extremely helpful. As I said, it's much easier to prove something when you have a confidence that it's true. OK, so how do we put everything together? So let's say, in an ideal world, we've understood all the complements from each level. So I have my x bar. I understand the cohomology in each one of these pieces. OK, great. Oh, well, we must be done. No. So if, when I look in my levels, I find fixed points for my action of x bar on any indecomposable summand M, or even worse, I find an H2, then, well, I've said it makes things interesting. I mean, that's the sort of polite way of saying that things get complicated. So if we're having a good day, the following happens. We use our calculations of each of the levels to bound the number of conjugacy classes of something. Well, that's interesting. We use our calculations to bound the number of conjugacy classes of non-standard complements we get in QX bar. So non-standard complements to Q in QX bar. And so we use, if we have enough torus, we'll be fortunate enough to get a finite number, so maybe 3 or 7. And then we go back out into our exceptional algebraic group, and we try, using other techniques, to find 7 or 3 subgroups which happen to live inside this parabolic that we're talking about and project to the levy as x bar. And then we check their action on the Lie algebra or the minimal module in the E8 case and see that they can't be conjugate to x bar. And then we don't have to worry too much more because we knew there were at most 7 and we went out and found 7. OK, that's a good end to our story. Unfortunately, if you remember back 25 minutes, The reason we were doing this is precisely because we could not get our subgroup in M3 to live inside the parabolic. So on those occasions where we've done all of this work and maybe our bound comes out as 2 or 1, we're not in such a good position to go out into the wild and find such a thing to put back in the parabolic. So we do need to have a slightly better grasp of things. And again, our hero has a positive impact on our bad day. So we can certainly use Magma to help us decide if these subgroups, so there'll be unipotent subgroups in Q mod Qi plus 1 that lift. We want to know whether they lift subgroups of Q. And if they're just a nice root group, then it's obvious that they're still a subgroup of the algebraic group. But we've come from L, the levy, where its trivials will be nice root groups, down to maybe some weird and wonderful subgroup X bar, and then it might be products of root groups, and yes, they form a subgroup mod Qi plus 1, but maybe when you start multiplying together, you get things in Qi plus 1, and then it doesn't become an actual subgroup of your algebraic group, well, of Q. And Magma certainly helps there. Similarly, if we have a non-standard complement to this thing in our sort of level, we just put it up to Q, we want to see if it lifts to a non-standard complement to Q in Qx bar. And there's lots of theory about this. It was developed by David Stewart in his PhD thesis. And loosely speaking, the way we can get Magma to help us is we just chuck in everything from Qi plus 1, and then, but with a sort of coefficient to tell us that we can essentially, using the groupably typed machinery, not in terms of matrices like Frank was discussing, it's much easier if you leave it sort of combinatorially in the groupably typed machinery, then you can ask whether you get a subgroup. And usually, if an H2 shows up in the right place, whatever that might be, then it turns out that you don't get a subgroup. And it's usually checking something really simple, like you just want the correct order for a unipotent element in that subgroup. And then all of the coefficients you put in for Qi plus 1 show up in such a way that they have to be something stupid that's not allowed, and therefore you didn't get a subgroup in the first place. Oh, good. My timer did change color. I mean, maybe it doesn't look like it changed color to you, but it certainly looks red on mine. OK, so we're on to the representation theory part that I sort of said I'd come back to. So there are some tricky cases that show up of I have my subgroup X inside M, and I want to understand how I restrict my M module V to X. So usually, I use composition factors and X1 groups between the composition factors, and then a finite subgroup calculation, and that is enough. But quite often, we really do need this last finite subgroup calculation. So what do I mean by that? Well, let's say I've got my composition factors, and I sort of have a guess that it's probably as bad as you would expect. So I've used all of my extensions. I have some module in mind. And then, of course, it's enough if I just find a finite subgroup of my algebraic group, which also acts, say, indecomposably on all of the parts I think it does, then that will be enough to show that my algebraic group must act that way. If it's only got sort of a choice of being indecomposable or it splits in some nice way, and you find a finite subgroup of it where it doesn't split, then, of course, it can't split for the algebraic group. But it wasn't always trivial to even construct M for our finite version of X, so that we can then use the metax on it. Again, not metax 64 or anything where I have to implement things. I want a button that I push, or type in direct sum decomposition and open brackets M. So I'm OK with that. That's enough of a push button. But not only that, we're sort of greedy. So we want to know how these non-GCR subgroups act on the Lie algebra and the minimal module. And in many cases, they actually do live back in M3. And you found a way of proving that. And then M3 has a nice action on the Lie algebra, and you restrict, and things are OK. Unfortunately, there are many cases when X doesn't live in any reductive overgroup. And then you're thinking, well, what are we going to do in those cases? So for example, when P is 2 in E7, back in the 80s, Liebeck, Saxel, and Testerman found infinitely many non-GCR subgroups of type D4. OK, they didn't call them non-GCR because The definition wasn't around for another 10 or so years. But they also somehow managed to give generators for each and every one of them. And so sort of work in progress is we think that using Magma, you can't then just ask for direct sum decomposition, because it's a bit harsh to ask it to do it for infinitely many subgroups at the same time. But using some sort of magic, we think we can actually understand those, even though we don't have a reductive overgroup. OK, so you'll notice that now the final slide actually matches the counter. That took me far too long to mess around with at some point to do that. But I thought it would keep people awake when they thought there was only 3 slides left. And actually, there were about 15. So is this the end of the story? Well, not yet. So there are still plenty of non-GCR subgroups to classify. It's not an advert. So Alastair and I have almost finished quite a lot of the cases. We do have plans to move on to the rest, or future PhD students, now that we both have jobs. But they're still not happy, these exceptional algebraic groups. Like, stories usually have a nice ending, but these seem a bit greedy, these exceptional algebraic groups. And there's still things like the non-connected subgroups, the finite subgroups from David's talk, and other things that we want to understand about them. And I will stop talking right on 45, Eamon. So.